After this lesson, students will be able to solve and graph multi-step and compound linear inequalities. Do now. Solve and graph the following inequalities. Don't forget that when you multiply or divide both sides by a negative number, you must reverse the inequality symbol in order to maintain a true statement. Pause the screen to try these 6 questions and resume when you're ready. 7b is less than negative 63. Divide both sides by 7, which gives you b is less than negative 9. To graph, we draw a number line. In this case, because it's less than and not equal to negative 9, we need to draw an open circle on negative 9, and the solutions of this inequality are less than negative 9. So I shade all the possible solutions. Number 2. Negative 7b is less than 63. Divide both sides by negative 7. Remember to flip the inequality symbol and graph. Negative 9 is not a solution of the inequality, so we draw an open circle on negative 9. Solutions are greater than negative 9, so we color the solutions to the right. Number 3. 2y minus 5 is less than or equal to 7. Begin by adding 5 to both sides of the inequality symbol, which leaves us with 2y is less than or equal to 12. Divide both sides by 2, and we get y is less than or equal to 6. Draw the number line. Since we're equal to 6, 6 is a possible solution, so we draw a solid circle on 6 and shade to the left. Number 4. Add 7 to both sides. We get 12 is greater than 3x. Divide both sides by 3. 4 is greater than x. For our final answer, we want the variable on the left, so we switch everything around. Our final answer, x is less than 4. Draw the number line. Less than 4 means that 4 is not included so I have an open circle shaded to the left. For number 5, our goal is to get x by itself. 5 is positive, so to get rid of it, I subtract 5 from both sides. This leaves me with negative x is less than 2. When we see negative x, we can think of it as being negative 1x. Negative 1 times x is less than 2. So I'm going to divide both sides by negative 1 in order to isolate the x. Since I'm dividing both sides by a negative, I need to flip my inequality symbol, and my final answer is x is greater than negative 2. Draw my number line. Negative 2 is not included as a solution, so it's an open circle, and I'm shading to the right. We have x's on both sides of the inequality symbol. My first step is to try to get all x's on one side. So I'm going to subtract 2x from both sides of the inequality symbol, which leaves me with negative 4 is greater than or equal to 2x. minus 1. Next, I can add 1 to both sides, which gives me negative 3 is greater than or equal to 2x. Divide both sides by 2, and I get that negative 1.5 is greater than or equal to x. For my final answer, I can flip everything around, so x is less than or equal to negative 1.5. Then I draw my number line. Negative 1.5 is included as a solution, so it's a solid circle, shaded to the left. Multi-step inequalities. Our example incorporates the distributive property. I'm going to begin by distributing. Which gives me negative 12 plus 3m, since I'm distributing negative 3 to negative m, is greater than or equal to 8m minus 28. I have m's on both sides of the inequality symbol, so I subtract 3m from both sides, which leaves me with negative 12 is greater than or equal to 5m minus 28. Add 28 to both sides, and I have 16 is greater than or equal to 5m. Divide by 5, which gives me 3 1/5 is greater than or equal to m, or m is less than or equal to 3 1/5, which as a decimal is 3.2. I can then graph this. .2 is included, and I'm shading to the left. You try the next problem, so pause the screen and resume when you're ready. We distribute negative 5 to negative 3 in positive d, which gives us positive 15 minus 5d is less than or equal to, we distribute 3 to 3d and negative 2, so we get 9d minus 6. I have d's on both sides, so I'm going to add 5d to both. So I have 15 is less than or equal to 14d minus 6. Add 6 to both sides. 21 is less than or equal to 14d. Divide both sides by 14. I can reduce by 7, so I get 3 halves is less than or equal to d, or that d is greater than or equal to 1.5. Draw my number line. .5 is included as a solution, and I shade to the right. Now we're going to talk about compound inequalities. Compound inequalities consist of two inequalities connected by either an and or an or. For example, if I'm talking about all real numbers that are greater than 0 and less than or equal to 4, I'm looking for numbers that fall into both of those categories, that are simultaneously both greater than 0 and less than or equal to 4. Written as a compound inequality, it would look like 0 is less than x is less than or equal to 4. I like to think of this as a sandwich, where our variable is being sandwiched. Plus, it's got the word and in it, so it's helpful to remember. When I graph this, I have my number line. Zero is not included, since it just says is less than x, so I have an open circle on 0. But x is less than or equal to 4. So the 4 is included, and therefore we use a solid circle. X is any number that is both greater than 0 and less than or equal to 4, which would be the numbers in between these two circles. So now I can shade that area. Our next example is all real numbers that are less than -1 or greater than 2. We use the word or here because there are no numbers that can be both less than -1 while also being greater than 2. So this is an either or situation. This is a compound inequality, so it is still considered one solution set, but it looks almost like two inequalities connected by the word or. When we draw it, it's on one number line, x is less than -1, so an open circle shaded to the left, than 2, or x is greater than 2. Open circle shaded to the right. Now I'm going to introduce you to something called interval notation, which is also known as universal set notation. Begin by graphing these 5 inequalities. So pause the screen and resume when you're ready. Technical difficulties. One moment, my computer's... Okay, sorry about that. Looks like my computer is not frozen anymore. So right now I'm just making my number lines, and then I'll go in and graph the inequalities. Okay, so for this graph, we've got an open circle on the -5, open circle on the 2, and it's an and compound inequality or a sandwich. The next one, closed circle on -5, closed circle on 2, and it's also a sandwich. Closed circle on -5, open circle on 2, and it's a sandwich. This is an or, so it's less than or equal to -4, so closed circle on -4, shaded to the left. Or x is greater than or equal to 3. So solid circle on 3, shaded to the right. Less than -4 would be an open circle shaded to the left. Or x is greater than 3, so open circle shaded to the right. Now for universal set notation, we're stating the solution set using maximums and minimums and whether or not it's included or excluded. For our first one, the minimum value in our solution set would be just greater than -5. So -4.9999999. Those 9s go on infinitely. So instead, we say -5, but use parentheses to show that it's not including -5. And then this goes until 2, not including the 2, so another set of parentheses. While this might look like an ordered pair, it is not. This is actually universal set notation, and you'll see from the next 4 examples that they all look a little bit different. For number 2, it also goes from -5 to 2, but this time both -5 and 2 are included in our solution set. So instead of parentheses, we use square brackets. For number 3, -5 is included, but 2 is not. So I can use one square bracket and one parenthesis. For number 4, where we have an or, our minimum is actually -infinity. Since -infinity is not actually a number, we use parentheses. Now looking at our number line from left to right, we start at -infinity and we shaded until we got to -4. -4 is included, so I use a square bracket. I use a U as a union to reunite with the right side of our number line. And on the right side, from left to right, we begin at 3, including 3, and our solutions go until infinity. Parentheses by the infinity, since it can't actually equal infinity. Our last one, we start at -infinity and therefore use parentheses. And it goes until -4, not including -4, so we use parentheses, U, and then 2, not included, up until infinity. In summary, we use an open circle for less than and greater than, and then we also use parentheses for the interval notation. When we have -infinity and positive infinity, we use parentheses. When we have a closed circle, or when we use less than or equal to or greater than or equal to, we use square brackets. So now let's practice solving compound inequalities with an AND. Be sure to reverse both inequality symbols when dividing by a negative. In our first example, we have a compound inequality that's an AND. Our goal is to get x by itself. However, this time the x is going to still be sandwiched. I need to get rid of the +3 and the ×2 using inverse operations. But instead of doing it to both sides of an equal sign, this time we're doing it to all 3 sides, which are separated by the inequality symbols. So I'm going to subtract 3 from all 3 parts. And I'm left with -8 is less than or equal to 2x, which is less than 4. Now I can divide each part by 2. And I get -4 is less than or equal to x, which is less than 2. I can graph this. include the negative 4. So it's a solid circle. We don't include the 2, so it's an open circle. And the solutions fall between negative 4 and 2, our sandwich. I also writing this in interval notation. So we start from negative 4, which is included, so we use a bracket. And we go until 2, which is not included, so we use a parentheses. You try the next question. Also graph the solution and write your answer in interval notation. Pause the screen to try it on your own and resume when you're ready. For this example, our goal is to get x by itself. So we have to get rid of the negative 1 and by multiplying by negative 2. To cancel out negative 1, we add 1 to all 3 parts. So I'm left with negative 2 is less than negative 2x, which is less than or equal to 6. Now I can divide each side by negative 2. By dividing by a negative, I have to remember to reverse the inequality symbols. Now this answer is okay, but I like to read from left to right, from least to greatest. So I'm going to take this compound inequality and flip it all around so that it reads as negative 3 is less than or equal to x is less than 1. Now I can draw my number line. We're including negative 3. We're not including 1. And we're shading in between. For interval notation, we're going from negative 3, which is included, to 1, which is not. Now let's practice solving compound inequalities with OR. Solve 6x minus 5 is less than 7, or 8x plus 1 is greater than 25. Graph the solution, and write your answer in interval notation. So again, for the OR, this looks like 2 separate inequalities, but it is one compound inequality separated by the word OR. So we can actually solve them separately, but when we write our answer, we're going to put it in one box. So I add 5 to both sides and get 6x is less than 12. Divide both sides by 6 to get x is less than 2. On this side, I subtract 1, so I have 8x is greater than 24. Divide both sides by 8, so I have x is greater than 3. Now for my answer, I write it as x is less than 2 or x is greater than 3, which is one answer, one compound inequality. When I graph it on a single number line. Two is not included, so I shade to the left. 3 is not included, and I shade to the right. In interval notation, I'm going from negative infinity to 2, and from 3 to infinity. You try the next question on your own, so pause the screen and resume when you're ready. Subtract 1 from both sides, we get 3x is less than 3. Divide by 3 to get x is less than 1. Add 5 to both sides, we get 2x is greater than 12. Divide by 2, we get x is greater than 6. Our answer is x is less than 1 or x is greater than 6. I graph it on a number line. X is less than 1, open circle, shaded to the left. X is greater than 6 would be an open circle, shaded to the right. And then for universal set notation or interval notation, we're going from negative infinity to 1 and from 6 to infinity. Sometimes you'll find that there are no solutions or that all real numbers would be the solution to the inequality. When we work on number 1, you'll notice something funky. Solve 7x is greater than or equal to 7 times the quantity of 2 plus x. I distribute my 7. 7x is greater than or equal to 14 plus 7x. I have x's on both sides of the inequality symbol, so I try to get them all on one side by subtracting 7x. But now I'm left with 0 is greater than or equal to 14 because the x's canceled out on both sides. So now I have to ask myself, is 0 greater than or equal to 14? Since this is a false statement, the answer would be that there is no solution. In other words, there is no value of x that I can plug into our original inequality statement that would make it true. If I were to graph this, it would just be a number line with no shading, since there are no solutions. Number 2, I would distribute and get that 2x minus 3 is greater than 2x minus 10. Try to get my x's all on one side. The x's cancel out and I'm left with negative 3 is greater than negative 10. This time, the statement is true. So the answer is all real numbers, which means that no matter what number I choose for x, when I plug that back into our original inequality, it will be a true statement. When graphing this, I have a number line, and everything will be shaded. You try these 2 questions on your own, so pause the screen and resume when you're ready to check. This is an AND compound inequality, so I subtract 1 for all 3 parts, and I get 3 is greater than or equal to 3x, which is greater than negative 3. Divide by 3 on all 3 parts, and I get 1 is greater than or equal to x, which is greater than negative 1. From left to right, I would like the numbers to go from least to greatest. So I flip the entire thing around. Now I can graph it. Negative 1 is not included. 1 is included. And I shade in the middle. And in interval notation, we're going from negative 1 to 1, not including negative 1, but including the 1. Number 2 is an OR compound inequality, so I solve each one separately, keeping in mind that it is one solution set. So I subtract 5 from both sides. Negative 3x is greater than 3. Divide by negative 3, so I have to flip my sign. Over here, this is the same as saying negative 1x is less than negative 4. So I divide both sides by -1, flip my sign. So my answer is x is less than -1 or x is greater than 4. I graph this. X is less than -1, so open circle shaded to the left, or x is greater than 4, so open circle shaded to the right. In interval notation, we go from -infinity to -1, and from 4 to infinity.